we have Erfan Rostami, the CTO of Voltai, which are building the AI for chip and electronics design, serving semiconductors industry. Thanks for having you here, man.
Of course. Pleasure to be here. Good afternoon, Paris.
Do you want to do like a short introduction of yourself? I think you're doing it best.
Sounds good. Hey, everyone. My name is Erfan, always having fun. Started Voltai 2 years ago with the belief that infrastructure is the bare bone for everything in AI. I was a researcher at Stanford University. Later, I worked at a semiconductor company called Ziegler Systems. They built a wafer-scale chip as big as my head. And that gave the passion to basically figure out how can we use reasoning models intelligence for designing complex electronics and semiconductors. And glad to be here.
Yeah, man. I think that's a great introduction. We've got some challenging questions, too.
Go for it.
For you. So let me start with so we've got the 3 sections for this panel. First of all will be the invisible bottleneck of hardware, where you'll be explaining about like what are the challenges when it comes to designing hardware. Second, AI native chip design. Let's talk about chips that have AI inside.
We can talk about that.
And the third one will be what it means for the physical AI builders. I would love you to expand and go more into details in that topic. But let's start with the invisible bottleneck of hardware. So the first question, you're a CTO of a company building AI for one of the most technically complex domains, right, on Earth, semiconductor and electronics design. So the question would be, for the people in this room, and most of them are actually building in the physical AI space and systems, why should they care about what happens earlier in the stack?
So the question is, why should you care about the electronics and semiconductors? A couple years ago when I started the company, the belief was that everything that we touch, from automotive, rockets, medical devices, and most importantly nowadays AGI, these are all things, in my view, bottlenecked by our abilities in innovating at the hardware layer. And fast forward 3 years later, we see that the world's most valuable company, NVIDIA, is a semiconductor company. Had you just invested then, you would have been rich by now. And the companies in this space who focus on this critical bottleneck have gone to change not just the economy, but also countries. TSMC has changed Taiwan. Shenzhen has changed Taiwan, has changed China. NVIDIA is changing United States. And I believe that for the next frontier as well, for, I guess, robotics, the folks who are going to be focusing on the very low level, the most complex part of the stack, which is the intelligence that runs on the hardware, the electronics and semiconductors. That's the part that would be the critical bottleneck, and whoever who's building in that will be the, I guess, most fortunate as well to benefit from it.
Yeah.
I guess that until 2030, 2031, my prediction is that the world is going to be mostly move away from being bottlenecked by power, being bottlenecked by silicon. And I guess TSMC being the biggest chokehold for the world continues to be one, while we have addressed many other bottlenecks. And I think that would be also true for robotics, where we have solved all the problems in the mechanical design, we have solved all the problems within the actuators, but then all of these mechanical aspects are the wrapper for the electronics part of it. And I think what Elon is doing with Terafab is the right thing to focus on, where long term, that is probably going to be the world's most valuable company.
Okay. Fair enough. Right now, when you look at the appliances and devices, like all of them are labeled with the AI stamp on it. Like, what does really an AI breakthrough in hardware design actually look like? From your perspective, from the CTO perspective.
Great question. So right now, when you look at the design process, traditionally it takes about 3 years. And this is why a lot of the silicon providers and hardware companies need to do the job of predicting the future, that the hardware that you're building today, is it going to be relevant 3 years from now or not? 4 years from now or not. But then the reason that it takes so long to design it is the manufacturing process actually takes about 6 to 8 months. But the majority of those 3-year period is spent on making sure that whatever you're designing is correct. The amount of logic is very dense and is very little, but if there is a bug, we're talking about billions of dollars in recall of the hardware, silicon, and electronics that you've designed, and then recalling them. So how about we can reduce that 3-year timeline into 9 months, into 5 months, where we no longer have to play the guess of where are the workloads are going to go into the future, where are the model architectures are going to be, what is the demand going to look like, where we can enter a more reactive mode, where whenever we see an architecture, a model architecture that's, I guess, getting more popular, being in the VLAs, the VLMs, and energy-based models, diffusion models, and all of that, we can change the underlying hardware as fast as possible. So we can deploy that to have the most efficient hardware to run the most efficient model. That is a paradigm that the world has not seen. To put it into perspective, imagine when we built the internet, updating a website would take 3 years. What would the world look like today? I don't think we will be here if updating a website was like this. It would take 3 years. But this is how it is in the hardware world, where the next generation of Kyber that we were talking about, Ultra Rubin racks that we're talking about, are going to take 3-4 years to get out there and then get updated. This is why I believe that the world is fundamentally bottlenecked by our abilities to iterate and innovate fast at the hardware layer, which is ultimately also limiting our ability to innovate at the model intelligence architecture.
OK. I think we are in a great space where people really get what you're talking about, especially in the physical AI space. I mean, these people are used to iterate over hardware, which is not as easy as iterating over software, of course. I'm sure they got your point very well.
Yeah. I mean, I think the other mental model to adopt here is that the ultimate user of these, whatever we're building here, being the models we're training, the robots we're building, the data centers we're commissioning, are actually not going to be humans. The ultimate user are going to be the agents and the intelligence. And that's when we enter a world of infinite usage, where we're no longer bottlenecked by our abilities in the number of people who could instantiate the agents to go do the work, but an agent could instantiate 1,000 sub-agents under itself to do the job, to do the task. And I think that's the part where the hardware becomes the bottleneck. And the models as well do the architecture exploration on what is the best model to train, what is the best intelligence to discover, rather than humans. And after that, the way we have seen in scaling laws, there is the number of parameters that matter, is the amount of data that matters. A lot of now the world is running out on data that is available on the internet, and we are relying on verifiable domains to generate data that practically will be better than humans. And I think that would be the ultimate test for intelligence, where we're no longer bound by the quality of the proprietary data that you collect from enterprises or humans, but actually we can generate the data based on the fundamentals of physics and the first principles of the world. And that is going to be all dominated by also the compute layer, where the compute is going to be the biggest contributor of generating high-quality data better than what humans can do. Mm-hmm. So both at the intelligence layer, where the agents will do the model exploration, will discover new architectures, and also at the data layer, I think that's kind of where there's going to be infinite demand for inference, for hardware, but then the world is going to be bottlenecked by silicon.
OK. Let's go back to the second part about the AI native chip design. Can you walk us through a specific concrete example of where AI native design tools change the outcome in actual hardware timelines?
Great question. I'm pretty sure you guys are all familiar with companies like Broadcom. They're a $2 trillion company. Actually, not a lot of people know what they do. They're very secretive about what they do. they're most well known for taking care of physical design, for building the AI accelerators for some of the world's most smartest companies. We're talking about the TPUs designed by Google. We're talking about Jalapeno designed by OpenAI, where they take care of the front end and the logical design aspect of things, while a lot of the back end and the physical design, when you have the logic, you need to turn it into like physical implementation at the foundries, is mostly done by Broadcom. Why is that the case? When you look at the node processes from TSMC for 7 nanometer and below, the error rate that you see produced by the simulation tools is about 15 to 20% error rate, meaning that whenever you have a standard cell and you have voltage going through the metal that excites the metal, creates an electrostatic field around itself, you can almost be sure that most often time when you like manufacture that piece of hardware, it's going to have 20% error rate that is actually wrong. And a company like Broadcom has decades of experience of manufacturing these things, so they know the guard bands in the design process, that how far they can push the limits on the physical design before they start failing, where they produce a silicon that is actually not functional and doesn't bring up, or has crazy parasitics and RC extraction, RC problems. They have capitalized on that knowledge and the IP that they've developed around this, hence why they have an advantage to be a $2 trillion company. And I believe that when it comes to being an AI native workflow, how does it change that process is when we can reduce that error rate and the architecture exploration that you do to less than 1%. The possibility of you turning the logic to the physical design and then having an error when you can do direct numerical simulation with AI that allows for higher fidelity and higher degrees of freedom of simulation, and for the AI to be able to do all the exploration around the architecture to get to an error rate than less than 1%, is going to enable designs in the future in a way that the world has not seen yet. Because the current status quo operates on a 15 to 20% error rate. But then if we can reduce that to 1%, we're going to see a lot of exciting designs.
Okay, man, perfectly summarized. Thanks so much. Considering we have so many physical AI builders and robotics builders here, I would love to focus a little bit on them in the last part of our session. So to all the founders and the engineers from the physical AI space, building humanoids, building industrial robots, and physical AI systems, what should they understand about the chip design layer that most do not? Is there a direct implication for how they think about the hardware strategy, specifically these people?
Okay. I will touch on 2 points on when it comes to like the physical AI builders in this room. The things that I'm talking about, what does that mean to you? So I will touch on 2 points. One is the extreme co-design across the stack. And the second piece of it is that I think the world is going through, the robotic space is going through the same wave of innovation that we're seeing at the data center space. So let's talk about the extreme co-design. When we look at the Intel Xeon 32 nanometer, the ratio of logic core to the LLC cache used to be around 70% that we had. When you look at the die, 70% of the die space was dedicated to logic cores, while the rest was given to more like SRAM and cache type of architectures. But then when you go to from 32 nanometer to 7 nanometer, that ratio drops to around 20%.
Wow.
Why is that the case? Is because like we had less logic per die area compared to the LLC cache, because at 7 nanometer and below, the level of thermal density that you get produced by the logic core was so high that you simply not be able to do the thermal removal from it as efficiently as possible. So people put less logic, and they put a lot more cache around the logic because that it's more, it has a lot more space around it, so it produces less heat. And so they just put more cache around the logic.
Yeah.
But then what happened was with the Grace Hopper designed by NVIDIA, they introduced the liquid cooling technology that allowed that ratio to go back up to 70% again. Meaning that a change at the data center architecture level, which was introducing liquid cooling and instead of air cooling data centers, allowed the designers, the chip designers at the very low level, and instead of being constrained by the thermal limits and then using less logic to like actually pack as much as logic while being able to remove as much as heat as possible. So let's take that analogy also for the robotics space, where, again, on the data center space, we saw that Google went to design their own TPUs. OpenAI went to design the Jalapeno. We see that Anthropic is doing a deal with Samsung to do the next generation of chips as well. And I think this is where the robotics is also going to go, where right now you guys are using the the Jetson chips. You're using the Qualcomm ones. You're using the Rock chip. And you're using off-the-shelf hardware. But if you're going to be a successful company, the lesson that we learned from Steve Jobs was the best companies in the world who like build the best products ultimately build very verticalized design, in a sense that the way that they built the best iPhone was eventually when they went to building, or the best MacBook was when they eventually like built the M1 chip, the M2 chip, the M3 chip, fully vertical integration to build the best product. This is what Tesla also did. This is what BYD is doing, and I think we will see the same thing with robotics, that right now everybody's using off-the-shelf hardware, but my hypothesis is that if we want to have robotics to run trillion parameter models with much more reasoning capacity, with much less latency and a lot less power, the builders have to like start building custom hardware and custom ASIC and custom PCB that gives you an advantage, a competitive advantage compared to any other, I guess, robotics and physical AI company out there. This hasn't happened yet because I think we're still like very much early in this process. The model architectures are not set yet, the VLAs and the VLMs. I think there's a lot of like change on that. But in future, if we want to have robots with extremely high reflexivity, I don't think we can like fully rely on just internet access and just like deal with the kind of problems that we deal. Like your iPhone, when you still like use it, it still struggles with changing network access between the Wi-Fi, the internet, and all of that. And if you're just relying on the cloud to do inference of intelligence to the robot, most likely your robot is going to be very low quality. The only way you're going to have the best experience is when you can do edge inference and do vertical integration of the model and then building custom ASIC for that, so you have low latency, low power, and high intelligence. And this is a trend that we'll see in the future, more and more of it. If you do that, we're here to help you guys. We build intelligence to build electronics and semiconductors. We have built a hardware team that is on par with the OpenAI robotics team. A lot of them used to be colleagues at Apple. Some of them went to OpenAI. Some of them came to Voltai. And if you have the ambition, the robot that you're building, you wanted to build custom PCB, custom ASIC, and all of that, we are here to help you.
Awesome. Man, that's fantastic. We are running a little bit out of time, but we've answered all the critical questions we wanted to answer and address. Thank you so much for coming here from SF, right?
Yeah.
So that was a long way. So ladies and gentlemen, that was the Erfan CTO of Voltai. Big applause for him. Thank you so much for coming again. It was a pleasure.
Thanks for having me.
Thank you.